right, a force field is a vector field that describes the force that would act on a particle at various positions. For the electric field, we're starting with gravitational field. For the gravitational field, we use the letter G, lowercase g, gravitational field. And the unit for that, if you remember, the net force equals mass times acceleration, where acceleration is g. So then solving for g, we have force per mass. Force over mass, Newton per coulomb. Per kilogram, excuse me. The electric field is the same thing. Except, remember, in our Newton's law of universal gravitation, we used masses. In Coulomb's law for electrostatic force, we use charges. So, electric field just becomes Newton per coulomb. Electric fields point in the direction that a positive test charge would travel. So the way this works is to determine the presence of an electric field, we have to take an infinitesimally small point charge that will always be positive, and we're going to place it around a charge. And determining whether or not that charge is repelled will tell you that you're within a positive electric field. If the test charge is attracted to your other charge, then you're in a negative electric field, because our test charge always has to be positive. Out from positive and into the negative. Out from positive into the negative. If you look at these lines, they go out from the positive and into the negative. All right, pause this, try it, label the positive and negative. Out from the positive, into the negative. Because wherever we put a positive test charge, if we placed it right here where my mouse is, then we know it's going to be repelled because it's going to follow these lines. If I place it here, it's going to be attracted. So I know this is a negative and this is a positive. Rules for electric field lines. Lines begin and end only at charges or at infinity. Lines are closer together where the field is stronger. Right, so the more charge or the more field density you have, the stronger the field will be. Larger charges have more field lines beginning or ending on them. Electric field lines never cross, since the electric field must point in a definite direction unless it's zero. And then finally, at any location, the direction of the electric field is tangent to the electric field line that passes through that location. So all of this really kind of sounds complicated. So let's break it down. Lines begin and end only at charges or at infinity. The lines are starting from the charge, right? From here. Or from infinity, way over here. That just means they have to start from somewhere. Okay, so rule number 2. Lines are closer together where the field is stronger. Way out here, in the outer reaches, the field is not as strong, because remember, it follows the inverse square law. The electrostatic force follows the inverse square law. The electric field lines are more separated out here. But as we get closer, you'll see the separation distance between them is a lot less. Larger charges have more field lines beginning or ending on them. All right, these are all equal. But if either of these were a larger charge, you would have more field lines. At any location, the direction of the electric field is tangent to the electric field line that passes through that location. That just, if we take a positive test charge right here, we know the electric field line is just going to follow this line, right? That's what rule number 5 is saying. That's all. Don't cross the streams. It's Ghostbusters. Try it for yourself. Equal charges. Did I trick you? Is that tougher than you thought? Right, so the lines can never cross, but they're going to repel near each other. Equal charges, so each one has the equal number of lines coming out, 7 on each side. Gravity as a field. By invoking his law of inertia, which says that bodies not acted on by net force move at a constant speed in a straight line, Newton concluded that a force exerted by Earth on the moon is needed to keep it in a circular motion about Earth, rather than moving in a straight line. He realized that this force could be, at long range, the same as the force with which Earth pulls objects on its own surface. So, gravity is a field. And if you are within this gravitational field, then you are falling towards the Earth. This is Newton's law of gravity. Later on, in 1905, Albert Einstein came along and looked to unify gravity and inertia. Because mass and energy distort the shape of space-time, Euclidean geometry of standard textbooks couldn't accurately describe it, so Einstein's general relativity uses a more complicated math built on the non-Euclidean geometry devised in the 19th century by, you'll know this guy, Bernhard Riemann. Riemann sums, right? Math class. Gravitational field distorts space around the mass that is causing it, so that any other mass placed at any position in the field will know how to respond immediately. Bigger masses are going to curve the rubber sheet, if you imagine this to be a rubber sheet, more than the smaller masses would. This is what it looks like. And then actually in space. So we have a bowling ball and golf ball, and then actually in space. This is Albert Einstein's theory of general relativity. In a nutshell, there's a lot more to it. I urge you to go look into it and research it more because it is extremely fascinating. But for us, that's all we need. How do we represent the strength of the field? More lines, right? More lines mean a stronger field. Bigger lines mean bigger field. So we have vector length, so stronger, and density, more. Either one is going to represent the strength. We have gravitational field strength to be force over mass. This is in topic 6.2, notice. And then we have acceleration due to gravity solved using Newton's law of gravitation. Right, so if we plug in this, or excuse me, if we plug Newton's law of gravitation in for this force right here, and we solve, we're going to get this, which represents G. Same thing for the electric field. Not electric field strength, but the force per unit charge. If we take Coulomb's law and we plug it in for F, we're going to get KQ over R squared. Representing acceleration is not the whole story. Lowercase g is the gravitational field strength. It is the force per unit mass.